Okay. Hi, everyone. Thanks for having me here today. I'm glad to be back. I was here last year and enjoyed it thoroughly. My name is Pierre Yves. I'm the CTO and co-founder at Exoscale. We're a cloud hosting company in Switzerland trying to make the lives of small companies, startups, and SaaS businesses mostly much simpler when going to the cloud. I'm also an open source developer. I do mostly stuff that revolves around the notion of visibility and monitoring, especially in Riemann, in Collectd, and such tools. But today I'll be talking about a bit of a different topic. So mostly the aim of the talk, even though it revolves around the notion of distributed systems, is to try and discourage you from building one from scratch. It touches specifically on the point of resource allocation in distributed systems and fault tolerance. I won't go in the details of the CAP theorem because I think that's a subject that many of you are knowledgeable about. I might not be the best person to address this, and it's not really relevant to the content of the talk. So a quick outline. Basically, the talk is separated into a bit of storytelling, introducing what we're building, how we build distributed systems, how we end up with a distributed system, because you're usually building a product, not trying to build distributed systems per se. Diving a little bit into Mesos, and then a library that I built that makes it easier to work with Mesos. All right. So how do we get there? How do we end up with a distributed system in the first place? Usually it starts with a simple idea, a simple product. Let's say that you're a company and you want to completely change the world by disrupting the job board industry, for instance, right? You're not happy with the current state of the system. You find that the software is too clunky. So you build your service, and it's usually going to start with a simple app, free tier. It's got a database, it's got a front-end server, and that's it. Even though there is a database, it doesn't fall into the accepted notion of distributed system, right? It fits in a single machine quite easily. So that's going to be your architecture. All fits in a single machine. You've got your database and an app there. And then you hit the first signs of success. You've got a bit of traction. Your single server isn't sufficient anymore. So you decide to adopt a simple scale-out technique. You put the database on its own machine, and then you spread out to multiple front-end servers. You do have to bring in a load balancer, and you have a few things that become a bit harder. Especially things like logging and visibility of the whole system. So you switch to a centralized solution. Your architecture now looks like this. It's still not within the realm of big distributed systems. It still fits into everyone's head. And now features get added. You need subscription emails, but you realize you cannot do that synchronously, so you have to push subscription emails out onto a queue and then send them out with workers that introduce a new technology into your stack, new types of machines. You also start a shift when you treat your machines from pets, like giving each machine its own name and tending to it manually to a cattle approach where you start introducing configuration management and start treating your machines as members of homogeneous clusters. It's still reasonable. Everyone can still figure out what's going on in your infrastructure. And then seed money runs out. Like your company doesn't have any money anymore because you built it on a freemium model, for instance. So you start reaching for monetization techniques. For this, you build a freemium model, so you need analytics on what's going on in your system. you need to run these analytic batch jobs somewhere, and you need to figure out where that is. You do partner with another company, but they use this weird PHP stuff that doesn't match your backend, so you have to run that on a separate machine as well. And that's, the infrastructure is starting to be a bit more complicated. You have machines with specific roles, specific configurations. It starts becoming a mess. And what you realize is that as your product grows, so does your infrastructure. And your infrastructure becomes a huge cost center. You have free Jenkins slave to build all your separate jobs and separate software. Metrics and monitoring in general goes on separate machines because your infrastructure is so complex that it needs separate machines to do this and to watch that everything is running properly. You need command and control to do operations because you realize that when you do them by hand, you eventually break stuff or end up with machines that are not homogeneous in a sense. You start using Puppet, and your ops burden is becoming quite huge. And if we take a step back, you're still ticking all the right boxes, right? You did everything right. You're DevOps, you have CI, and you have infrastructure as code. So what went wrong? First, your resource utilization is probably quite low, and that's a problem because most of your utilization might be artificial. You have agents that run on every node to perform monitoring tasks, for instance, and that eat up your global utilization. You have peaks that you have trouble dealing with. And by that I mean that if you're at 20% utilization globally on your cluster or on your set of machines, you still have peaks that you cannot handle because they're located on very few instances in your infrastructure. And adding new services or adding new components to your infrastructure becomes harder and harder. You constantly have to make allocation decisions. Which machine should that service go to? Or should I co-locate this service or this batch job with my front-end servers? Should it go on separate machines? And you always have to juggle with allocation. The second question is that you end up with Puppet or whatever configuration management solution that you choose being the repository where you spend most of your time working and most of your time evolving, which means there's something that's wrong because you should be spending more time building your product. And last, handling failure is really hard. Your monitoring system will tell you when something goes wrong, but then you have to act on it. Maybe a machine disappeared, you have to spin up a new one if you're on the cloud, or actually provision hardware if you're still running on-premise. These recreating machines is a step that's a bit involved, and you end up having to do allocation decisions again. So, but if we look at it from a service perspective, you drew a picture that works, right? You have these clusters that make sense and that have specific roles. You have your product cluster that runs really the core of the product. Your infrastructure one that helps you build and run your service. The monitoring one and the data one, which provides you with a persistence layer of sorts. So what would be nice is to be able to co-locate and these different types of services or type of machines on all your infrastructure, and as utilization shifts, being able to just reallocate dynamically from a machine to another, or spin up new machines and start utilizing them. So if we look at the current spectrum of technology that allow you to do that, containers are a big topic, but they still require you to do a lot of stuff by hand, right? Containers that just give you an abstraction that's easy to apply to collocate isolated processes on a single machine, right? But you still have to do the allocation yourself. Private paths solves that problem completely, as does public paths, but usually it gives you a sort of constrained environment, right? It gives you an environment where you're going to have to play by the rules of the path, which you might not want. And then there are cluster allocators, of which there are several, but today we'll be talking about Mesos. So what we're going to address is how do you get out of the job of shuffling machines around and making allocation decisions, right? And that's where Mesos can help, and we'll dive a little bit into that. So, first things first, Apache Mesos says that it abstracts CPU, memory storage, and other compute resources away from machines, be they physical or virtual. And it enables fault-tolerant and elastic distributed systems to easily be built and to be ran effectively. It's got a three-component architecture. Right now, it relies heavily on Zookeeper. And then you have masters and slaves, which are plain Mesos processes, simple C++ processes, and frameworks, which we'll dive on, which sit on top of Mesos and make allocation decisions. In detail, you have masters that coordinate, you have slaves that expose resources and report to their master, and then workloads called frameworks, which come and sit on top and talk to the master to produce tasks on your architecture. Mesos master, they expose a simple HTTP and protobuf API that allow a sort of actor model that's used by Mesos throughout the entire architecture. It exposes a web UI for you to see how your cluster runs. It's the main entry point for frameworks. That's how they come and sit on top of Mesos. And they gather and they maintain slave availability, and they take the decision to offer resources to frameworks. Of course, the whole infrastructure is highly available and can be horizontally scaled. Mesos slaves, they're used to launch tasks. They're just machines that are here to be instructed to run payloads. Right? They expose their resources, and they can expose CPU, RAM, but also more complex resources, attributes and labels, IPs, and network ports, for instance, and even storage volumes. Frameworks, they're software which instrument workloads on a Mesos cluster, as I was saying, and they're composed of two internal components, the schedulers and executors. Schedulers, they're the main entry point for the application or the service that the framework provides. They interact with the master, they receive offers, and they receive task statuses through the master. And they're the ones who are responsible for launching tasks and picking up on the offers that they were given. So they're the ones who are actually making the allocation decisions. That's the main job of the scheduler. They're also responsible for exposing services if there needs to be a service exposed. And then executors, they're just helpers to actually run the payload on slaves. They manage workloads, they can report status to the master, which will itself report it to the schedulers. They're totally optional because Mesos is also able to spin up tasks by itself, but you get a little less functionality if you go this route. So again, that's the architecture that you end up with. You have these frameworks that are in green that talk to the master and deploy executors on slaves to actually run tasks. If we spend a bit of time on the offer-based allocation model that Mesos relies on, a scheduler, it will just receive a list of offers coming from different slaves handed out by the master. It decides which ones it wants to pick up It makes the decision that it's going to be running on this slave and take up that amount of resource. It reports that decision back to the master. It's going to receive updated lists of offers, and it's able to launch tasks on the resources that it picked up on, right? The actual list of offers that you're going to receive is decided by the masters, and it's its main job to give you an appropriate list of resources so that you don't end up eating up all the cluster. So the scheduler itself has a lot of responsibility. It has to make this allocation decision. It has to instrument launching tasks. As far as tasks are contained, there are two main types of tasks right now. The first one is running in Docker, launching actual Docker containers, and the other one is a level above and is running within C groups, which is the technology that Docker builds on. So Mesos is also able to spin up processes that are just C group contained. Just a few additional properties. Tasks, they may provide health checks to let the master make sure that it's running properly. They may ask for stuff like port forwards, persistent storage volumes, and a few things like this. If we look at the list of notable frameworks of sorts, Spark is the original one, but then Marathon is one of the more well-known, which gives you a sort of private path that can run arbitrary containers, and which is quite convenient. Chronos is a sort of distributed cron for running scheduled tasks, for instance. Then you have a few applications that have built Mesos functionality within the application and itself, such as Jenkins, which is able to launch builders as Mesos slaves, as Mesos tasks. Sorry, Hadoop, Apache Kafka, and Apache Cassandra also provide that ability. All right, and that's it for the general presentation of why you might need Mesos and what it's able to do. I'll spend some time now showing you code, mostly in Clojure, that sits on top of Mesomatic, which is a library I built to help building frameworks. It's got a simple dependency list. Just relies on you've got a plain library and an async library that's able to work with Clojure core async, which gives you a bit of an equivalent of the concurrency primitives that you have in Go. But first, why would you want to build a framework if you have frameworks such as Marathon or Aurora or Chronos? There are a few instances where it makes sense. I think the most evident one is when you're building a product that operates as a service and that needs specific resource allocation when you have new customers. In that type of case, Mesos really can help. You also might be a bit too constrained, or you might not be able to work with the current frameworks available. And I built this as a library versus building yet another framework, because if you need several Mesos frameworks, there are a few common decisions that you're going to be doing again and again within all frameworks. And this is why this was built as a library. So the components of the library is having a simple Clojure facade for types to make it a bit easier, because otherwise you're dealing with protobuf structure and serializing and deserializing from and to protobuf all the time, which can be a bit tedious. There's a facade for creating schedulers, one for creating executors. There's a core async version of these facades that help you with if you want to deal with Mesos in an asynchronous manner, which we'll see. And then there are allocation helpers to help you make these allocation decisions I was talking about, and which are the main responsibility of a Mesos framework. I'm not going to spend too much time on the type facade thing. It just helps you. There are just 3 simple signatures that help you convert to and from Mesos types. The cool thing here is that when in the Clojure world, that allows you to work with plain data, plain maps, and not deal with protobuf classes. But what we'll be looking at is the executor and scheduler facade, and that's also going to showcase how you actually deal with building a framework. So everything is protocol-based, which in the Java world would mean that everything works with an interface in that facade. Your client code just has to realize that interface or that protocol in the Clojure parlance to receive input messages from the master, and then you're given a driver which helps you emit messages back to the master when you're building a scheduler or an executor. So when you're building an executor, that's the type of signature that you're dealing with. Your responsibility as a builder is just to implement the interface that's on top, which means that you have to react when you receive the message that you've been disconnected, that there was an error, that you're receiving a message from the framework, so most likely from the scheduler, that you need to kill a task to launch a task, that you were registered, re-registered, or shut down. And what you can do as an executor is abort, say that you're joining, run your driver, but mostly send framework messages or send status updates. That's usually the 2 signatures that you'll be using the most. So most likely your input will be launch a task or you receive a framework message, and your output will be sending a status update or a framework message. It's very alike for the scheduler facade. You have a very similar interface to implement and a very similar driver that helps you interact with the master. Most of the input will be receiving resource offers, knowing that an offer has been rescinded, which means that it's not valid anymore, receiving a framework message or receiving a status update for a task. And as far as most of the tasks that you'll be doing, it's launching tasks, killing a task, reconcile task, which means asking for all task statuses, and requesting resources, meaning you realize that you don't have enough resource for your workload, so asking the master to send you an updated list of resources if possible. So what it comes down to for most of the work is that you receive resource offers and you launch tasks which pick up on these offers. If we look at what a resource offer looks like, in the Clojure world, once it's been transferred, you receive a simple map, and that map tells you what slave the offer comes from, and what type of resources in terms of memory, CPU, storage, or network ports are available. And a task is also a simple map. When you're just using the plain C groups support and not going to Docker, you assign resources to your task, saying how much it will consume, and you give it a command, and that's just about it. For Docker containers, it's really similar. You also have that resources key in your map, but you'll also need to specify the container image that you will be depending on. Right, and before diving into the actual building of a framework, I'll just show how the core async facet work. Basically, it works exactly the same. The only difference is that the messages, you want to receive them with an interface that you're realizing. you will receive them through a channel. So you create a channel. Does this work? Yeah. You create a channel. You build a framework that's asynchronous and that builds on that channel right here. Give it a name, and then you can just start your framework. And here I reduce on the channel, so I augment state by calling handle Mesos message on the channel. And my initial payload is a driver. And here I dispatch handle Mesos message on the type of message that I was receiving. Last thing in the library is the allocation helper. It's, again, protocol-based, but there's only one implementation for now. What you give it is a list of tasks that you want to run, the list of offers that you received from Mesos, and it will help you and tell you what the best solution is to run. There's a single, again, a single implementation of the allocation helper. It does help you account for common problems that you might have, such as you want 6 instances of a task running, but you don't want more than 2 on a single host. And that's, which is a very common need. For instance, if you're running front-end servers, you want to spread across several slaves, right? A few additional task fields that I show here to help with this is max call means max collocation, and how many tasks of that type you want. And that's the only thing that's needed for the allocation helper to do its job properly. All right. In the remaining time that I have, I'll show how to build a simple one. Let's say that we have a static configuration of jobs that we want to run. I have these 2 jobs that I want to run on a specific schedule. Apart from that schedule key, it's mostly a standard task definition for Mesos. The only state that I will be keeping throughout the life of my framework are the jobs that are currently running. So I'll keep them in a set, and that's the closure simple form for set, and my driver as given by the framework. Ticking, I can rely on a library that does that for me. That's not the aim of that talk. And what I can do is just send a message on a channel by doing put on a channel every time I tick. So every time I tick, I send a new message on the channel, and then I can build my framework like this again, doing a dispatch function that will be called every time a message comes in on the channel, and reducing with that function on my initial state. Here, I also started on the same channel. I also started the ticker, so I will receive 2 types of messages: the messages from Mesos and the messages from the ticker. And that's what the structure of the program will look like. You'll have this channel that has 2 inputs, and that's able to produce messages out back to Mesos whenever it's needed. So handling resource offers just means associating on your internal states the offers that you've been provided with. Whenever you tick, that means that you should be running a new job. What you can do is check if the set of currently running tasks contains the task that allows you to avoid running a single task twice and avoid overlaps in runs of tasks, and then use the allocation helper to get an amount of offers and an amount of tasks, and just launch these tasks. So that's, that stays quite simple and terse, but essentially that's all you'll need. One of the last bits is updating status info, where whenever your status is running, you'll get that message, so you can update your state of running processes. And whenever it's not, well, you can just remove it from that set, and that allows your internal state to remain constant. And that's all there is to building a simple framework. And we actually have an internal cron-like thing that works in just about. That's just about how it works, really. The question when you see a simple interaction like this is why we would build it in Clojure in the first place versus, I don't know, there's very good support in Java, in C++, and in Golang, for instance. One of the first things is that it's really easy to build this as a library, and Clojure has this library-first approach. And the second part is these very good facilities that you have for making good decisions. And we'll see a few. Here, I'll show you how using observable atoms in Clojure and core match and data diff can help you make very simple and clear decisions. As for the atom, in our example framework, we used a static map. You most likely will have a configuration that can change dynamically. If you store that configuration in a Clojure atom, which is basically an observable, mutable structure with a really clear contract on when mutation can happen, you can watch that atom to converge your new topology change. And here I just use a simple library that watches the config and updates the atom. So converging the topology would be making decisions from the old state and the new state. Because when you observe an atom, you receive the old version of the atom and the new one. And here, with these two configurations, the previous and the upcoming one, you're able to diff on the two and take decisions on what you should do with that difference. Here, what I do is I have a pure function that does absolutely nothing except tell me what side effects should be produced when going from the old to the new, and then I run through these side effects and perform them on the channel. As far as the decision process is concerned, I'm using data diff to see what was before and what was after. I'm just looking at what's changing. When things changed, I call that function. And this is one of the very interesting cases of Clojure. It has this wealth of libraries, especially this pattern matching one, which allows me to match on my old runtime and my new runtime, just in case I change from a C group container to a Docker container, for instance, and the previous status to the new status. And with the pattern matching function, I can just say, whenever I go from stop to stop, I have no side effects. Whenever I go from start to stop, my side effect is to stop the task. When I go from stop to start, I should start a new task. And whenever my runtime change, I should stop the old one and start the new one. And this is something that you can most likely do very simply with a switch case or an assortment of if-else statements. No problem with another language. But here, in a few lines of code, I can have a very clear way of making my decisions and introducing new decisions. The output here is just a list of side effects. And that's why here I'm just performing these side effects. The return will be here and will be called by perform side effects. So the structure of the program will be just this. Having the HTTP or file system produce configuration onto an atom that's observed, decisions will occur whenever the atom is modified, and then a change is produced on the channel, which goes back to Mesos. And that's just about it. To wrap things up, Clojure really helps here because of the decision process that can happen and be simplified by these libraries. I think core match, especially the pattern matching functions, bring a lot of clarity to the table. Most of this is taken from a framework that we actually use. And again, immutability help. Here, my actual state is an immutable data structure, which means that there's no way for stuff to change under the table. I always have a clear picture of the world whenever I take a decision. Mesos really helped. Using Mesomatic makes it very easy to ensure that what's actually running on your production is what you expect to be running, and have clear insights when that changes. And what we're seeing is that leveraging Mesos, our operational burden is really reduced because there are a lot of decisions that we don't have to make anymore. As far as future work is concerned, Bundes is a bit in the works for us, but could be improved. And I think a pure JVM Mesos client is something that we're looking into building, because right now it's wrapping around the C++ library, which isn't always ideal. And I mean, that's about it for me. If you have any questions, I'm happy to take them. Thank you.